So, poop dimension. Do I get out of here like the next morning or some shit? Get it? Shit. Be right back. Right. Phew. Great experience. Now we ask some important questions. For example, where was I? What is a dimension? Let's have Matej Pavsic, one of the greatest living physicists, answer that question.
How would you define a physical dimension?
Look, if one considers a physical object, one can approximate it by a single point. If looked from very far, it indeed appears as a point. Just recall the picture of the Earth taken by, I think it was Pioneer probe, space probe Pioneer, when leaving the
Yes.
solar system. The Earth was just a point. Also, stars are just bright points in the sky. Their position on the celestial sphere are given by two numbers. Their distance from the Earth is the third number. So, to determine the position of any object requires three numbers. Those numbers are associated with three independent spatial dimensions. Dimensionality of a space is given by the number of parameters necessary to determine the position of object approximated as point.
Now that we can comprehend what a dimension is, let's look at how many of those are there in the universe. Turns out, we don't know yet. Bruh. However, there are some theories. Let's start with our bestie, Einstein. Looking at the theory of relativity, we learn that time is the fourth dimension. According to this theory, the space-time fabric curves around any object that has a huge mass or a huge acceleration. A four-dimensional universe, such as this one, would allow us to move through time, backward and forward, and in the three spatial dimensions. As we look at other theories, we see string theory. It proposes the existence of tiny vibrating strings as the fundamental building blocks of the universe. The basic idea behind string theory is that there are these one-dimensional strings with radius of Planck lengths that vibrate in specific manners to give rise to bosons or forces and particles or quarks and leptons. There are various bits in the string theory too. For example, the superstring theory, which by the way does not mean big strings. So, turns out string theory is more than Ron Carter's music album for sure. It stands for supersymmetric string theory. It incorporates both particles and force carriers to explain gravity. But wait, don't we already know gravity? Isn't it the Newton's apple thingy? Turns out science still does not know about the phenomena of gravity that we learnt in 4th grade. Stuff pulls stuff, unlike you who doesn't pull anyone, but like, how? Einstein suggested that space curves around mass, and that's how gravity works. While that does not match the quantum physics part where all forces are carried by particles. String theory is a chance at figuring out quantum gravity so we can connect both the theories and explain all fundamental forces of the universe, which by the way are electromagnetism, gravity, strong nuclear and weak nuclear. Anyway, back to the different string theories, we have the M theory. The M in this stands for membrane. The M theory is a combination of all the various string theories and is our closest theory to the theory of everything or quantum gravity. It suggests that there are 10 spatial dimensions and one time dimension. Now, where are these 10 dimensions? We have only height, width, and length, right? Or maybe even time. Turns out you are wrong again, bastard. So it turns out these extra dimensions would be really, 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 really small. These dimensions would be curled up and invisible to us, like some John Cena shit. They would exist only on the level of strings and allow them to curl up in more dimensions. This way, they would be able to give rise to more particles too. But what does this mean for us? Why do we care? I don't give a shit, though. How might we interact with these hidden dimensions? One intriguing possibility lies in the realm of quantum mechanics. Quantum theory suggests that particles can exist in a state of superposition, occupying multiple positions simultaneously. Could it be that these particles are traversing through higher dimensional space, moving beyond the confines of our three dimensional reality? It is a possibility. Now, some theories suggest that time also has three dimensions. We have our understanding of the first dimension of time. It is the past, present, and the future. But what would moving sideways in time mean? Would it mean exploring how the world could have been in an instant? Let's have Dr. Matej answer that question for us.
Yeah.
So let's say time is multidimensional and an observer moves sideways in time, where let's say like there is the length, right? The length is past, present, and the future. And an observer moves, let's say, sideways. So would the observer say the same present but different possibilities of the present? If not, what would the observer notice?
Yeah, it depends on how it will move. I will say later more precisely, but now let me say the following. Even if time is multidimensional, usually an observer would normally experience a linear, sequential passage of time. This means that his world line would be one dimensional. His present would change from from this hour to next hour, from today to next day, just ordinary passage of time with different layers of present moment. What he would see would depend on the direction of his motion in the multidimensional time. If I move slightly differently, then perhaps I will not go to the trip tomorrow, but I will stay at home and so on. But this would still be, according to me, just a normal, passage of time, normal sequence of possibilities. But okay, let me first illustrate the situation in the usual relativity, in which time is one-dimensional. So what we have in usual relativity? In usual relativity, we have four-dimensional space. Time, I depicted here three coordinates, time coordinates, and two spatial coordinates. Now, uh, the present is given by this surface. Here is two-dimensional, but actually it is three-dimensional surface. On this three-dimensional surface, there are moments of now that we experience now. Okay, there is a problem because we experience in light cone, but in our immediate surrounding, we see three-dimensional surface because the speed of light is very fast. Okay, but what then happens? Um, this surface moves in space-time, and when it moves, what is that? Here you have a world line in space-time, and if this surface moves, the point, the cross-section of the world line with this three space lies on different position on this surface sigma. Simultaneously surfer or spatial hypersurfer, this is 3D now. Uh, and it, as I said, it moves in the forward direction. And when it moves, it fills the space-time. In the usual relativity, space-time is block space, and this movement of simultaneity is in fact considered as illusion.
Now, let's figure out the different space dimensions. The first dimension is length, the second dimension is width, and the third dimension is height. But what is the fourth dimension? Okay, let's take a step back. The fourth dimension to us third dimensional beings is what the second dimension would be to the first dimensional beings. Here's a low quality clip of me explaining that using MS Paint. Let's see how this works now. The square is a two-dimensional being and the lines are one-dimensional beings. And for the sake of this, we'll say that the lines can only see in the frontward direction where their eyes are located. So let me draw small eyes over there. These circles are the eyes. I mean, one eye is enough, right? It's like a one-dimensional being anyway. So like these are the eyes. But now, obviously, the square has a specific length in this dimension that they will see. But now this is where something very interesting happens. The square can turn, right? And now its length in this singular dimension increases. And in fact, it can not only turn, but it can also go through it, because it can go through the line like this. And that is very interesting. Let's check it up further. Now, what would three-dimensional shapes look like from a two-dimensional perspective? To illustrate this example, I have what you would consider a rectangle on the screen. But is it a rectangle? No, it's a cylinder. Now, this is a two-dimensional screen, and this is the representation of a three-dimensional object. That's why we can make it look like various things. Let me give another example. So we ensure that the entire shape is in this dimension, and then it looks like a circle now. And obviously it's not, as we can see, it's a cylinder. So the shapes can change in size and figures. Now that we know how different dimensions work, let's look at the fourth dimension, or at least try to. So we are three-dimensional beings. This means that fourth dimensional beings would be able to look and get inside us without tearing through our skin. And that's creepy. So let's take cubes for example. A 4D cube called a hypercube or tesseract would be changing its size in our perspective as we look at it from different angles, or maybe it rotates or turns around. As a cube can be drawn by connecting two squares, the same way a hypercube can be drawn by connecting two cubes. Now let's take it to a new level and explore another 4D figure. This one's called a client's bottle. And no, you cannot store beer in it. Speaking from experience. Here's a 3D representation of client's or clean's bottle. For the four-dimensional view, the arrowheads would never touch the bottle, which can be seen happening near the intersection, hence proving that we cannot really, as three-dimensional beings, experience any four-dimensional figures or objects, assuming that the fourth dimensional is a spatial dimension and not a time-based dimension. Okay then, I heard bottle. I go drink. See y'all besties next time. Keep sciencing.